I get the impression that you have done that last video about timescales because we're going to start talking about how, how we get to some of those longer kind of the things you have to wait longer to get to, those caches and memories and storage and all that sort of stuff. So what are we going towards here?
That's exactly right. Well, yeah, so I've alluded many times to this large memory array inside the computer that's, made up of what I call pigeonholes. And nobody really knows what those are, but like these sort of like cells that are that you can put a number into, and I've sort of said the robots go off and get numbers out and come back and whatever, and that's very much useful to understand the principles behind it. But nowadays we're talking about staggering numbers of these pigeonholes. Your average computer's got 8, 16, maybe 32 gigabytes of memory, which is an awful lot of boxes. And unfortunately, we don't live in a panacea where it's like very quick and fast to get access to the memory cells. And so there's many tricks and techniques to sort of get some speed back from those cells. But I want to talk a little bit about how those memory cells actually work. There are predominantly two types of memory inside your computer, and when I talk about memory here, I know that there's some confusion sometimes, but like I'm not talking about your hard disk or your NVMe drive or your SSDs in there, which is storing like permanent files and things. I'm talking about the memory that your computer's using while it's running to store information, the picture on the screen that's currently there, the programs that are running, and those are the sort of 8 gigabytes worth of memory, that kind of feel. So that memory here, and we call that, that's volatile memory, because if you take the power out cord out of the back of your PC, as I'm sure you've at some point inadvertently done, then you find out that memory's all gone. It's very volatile. Whereas the other stuff's non-volatile. And we're going to be talking about volatile memory today. And there are two typical types of memory. And the first one is the most sort of obvious one from an electronic standpoint. And it is based around something called a flip-flop, which is not, in fact, a shoe, at least in computing.
And we did a video, and I think I used a flip-flop as part of the animation.
With a D flip-flop, we can store a single...
So the flip-flops are fantastic, and I have a picture of one over here, which unfortunately I would love to have drawn in real time, but I am too terrible at artwork, and I would get it wrong. But I want to quickly go over it, not because it's that important to understand it, but just to sort of get an idea of how complex just one bit of this memory is. It's made out of 6 individual transistors, and this sort of middle section here is the bit that's storing the oneness or the zeroness. And what it effectively is it's 2 inverters. So that's like a logical NOT. So if a 0 goes in one and a 1 comes out the other side, or a 1 comes into one side and a 0 comes out the other. And it's as if there are 2 inverters that are plugged into each other. So there are 2 possible stable configurations for this. Either there's a 0 going into the first one, which means that there's a 1 coming out of it that goes into the second one that comes back out as a 0 that goes back into the first one, and now it's kind of settled. Or the opposite, there's a 1 going to the first one, which means a 0 comes out, which means a 1 comes out the next one, which goes back into the original one, right? So you can see there are 2 possible ways that can hold and be stable. And that's effectively what this middle section is doing here. There are 4 transistors. 2 of them have these inverters here. This is like a CMOS and CMOS, where there's NMOS and PMOS, but that's a whole very deep rabbit hole. But very cool. And then effectively, once it's been set up, if we want to read the information that's stored inside that cell, we need to sort of turn on these access transistors, because transistors are like little switches in this particular instance. So by putting a little bit of a voltage on this top line here, we're connecting the outputs of the bit to the rest of the system, the data line that flows out of this bit. And it's a sort of coincidence we get both the value that's stored and the opposite of the value that's stored. We don't usually necessarily care about this side. We just want the bit, and this would be either a 1 or a 0 that's stored. Fantastic. And if we want to write the value, if we want to change the value that's stored inside this flip-flop, we do the same thing as if we're going to read, except we sort of push voltage back down the data lines, and the transistors in here are weaker than the ones that are in the rest of the chip, and so we can overcome the state that the flip-flop's in and pop it into the opposite state, or the state that we want it to be in. So that's cool and all, and fantastic, and we don't have to go into too much detail in here. It has 2 stable configurations, and the main issues to sort of consider about this is that this is on all the time, right? These are plugged into the power supply, and this is ground here. And even when we're not looking at the memory, it's taking a small amount of power just to keep it on. And that power budget adds up when you've got billions and billions and billions of these things. And so it's not really tenable for large amounts of memory. We can't afford that amount of power and sort of thermal dissipation. That's usually the issue. The more power it takes, the hotter it gets, and then the bigger your fan has to be on the side of your chip. It is instantaneous. For some definition of instantaneous, these transistors flip in like femtoseconds or picoseconds, like very, very tiny amounts of time. So I can get access to this bit very quickly. And when I want to change it, it's incredibly quick. So this is perfect for some of the information that's stored directly inside the CPU itself. So the registers, those things we've been talking about, the little piece of paper with the numbers that the computer's actually working on, are made out of arrays of these kinds of things. And we've talked a little bit about caches, and we'll get back to that in a second. The other thing to note about this is that there are sort of like all these sort of jump over wires that I've got here. So it's kind of complicated. There are 6 transistors and the wires cross each other. And of course, when you're talking about an integrated circuit that's made up of these things, you can't print 2 wires that cross because they will touch. So now you need 2 layers of that circuit so that it can go up and above the wire. So literally, as I've drawn them here with a little hop in it, that's what's going to have to happen somewhere in the chip design. So they're awkward to lay out. Obviously doable because they're in your computer right now. There is an alternative way of storing memory that is a lot more efficient in terms of numbers of transistors and things. So that one I can draw because thankfully it's a lot simpler. So we call this static RAM because, well, actually, it'll become obvious when I do the opposite of that, which is dynamic RAM, which is what I'm about to draw. So dynamic RAM has, we have a data line. Just as before, this is the data line that can read whether or not the cell is set to 1 or a 0. And we have one transistor here. And we have the address line that says, hey, I'd like to read this specific bit. And then off this side of this, we have a capacitor. And my drawings are not very good, and I may not have got exactly the right symbol there. And then it's just plugged into ground on the other side. So to store one bit of information, we have one transistor and one capacitor. Now, integrated circuits we don't really think of as containing anything other than transistors, right? But as it happens, the way that these transistors work, this is actually a capacitor. This plate and this gate part of the transistor is a capacitor, so we can just sort of make a bigger one. And now we've got 1 bit. And so the way that this stores a bit is to put a 1 in, we turn the address line on, and we charge up the capacitor. And the capacitor is like a tiny, tiny little battery that will store a little bit of charge for some amount of time. And then once it's charged up, we disconnect it, we turn off this switch, and now it's just going to sit there, and it's a little charged battery. And if we want to store a 0, we do the same thing, and we discharge the capacitor. We set it to sort of 0 volts. And you notice there's no crossing wires in this. There's no like things that are higgledy-piggledy. So this is a single layer, mostly. We can just replicate this millions and millions and millions of times in a row. We've got our millions and millions and millions of bits. So what's the catch? Why don't we make...
We're waiting for the problem, but
What's the problem here? Well, the trick is that name, it's dynamic. Now, and dynamic sounds cool and interesting, like the dynamic duo or the dynamic... But in this instance, it means it changes by itself.
The capacitor discharges, right? Yeah, okay.
Exactly. So, yeah, at this rate, when we're talking about the scale that we're talking, when we're putting billions of these on a single integrated circuit, this capacitor is absolutely tiny, and so its ability to store charge is also incredibly tiny. We're talking like dozens of extra electrons on top of one of the plates is now a charged capacitor compared to, what you might think of when you see those huge like cylinders on your circuit board that are like power capacitors that can store huge amounts of charge. This is nothing. So, that is kind of a problem because, yeah, as you say, it will discharge kind of by itself. So that means that if you come back to it a bit later on, and by a bit later on, I mean like tens of milliseconds later, it maybe is leaked out. And now it's not, you don't even know if it's a 1 or a 0 anymore because it's like somewhere in between. The reverse problem is possible too. These are packed into the chip so tightly that when the capacitor leaks, it might leak into its neighbors and actually charge them up. Right? They're that close to each other. We're so close to sort of magical quantum things going on. So this needs care and attention. And that care and attention requires us to periodically go back and recharge all the 1 bits to be 1, and to re-discharge all the 0 bits back down to 0 in case they've picked up some of their neighbour's charge. There's a sort of another subtlety to that, which is that in the domain of our wonderful static RAM here, when something is on, when a transistor is on, it's exactly 3 volts or whatever the voltage is inside the system. It's like a logic but 1. There's no question about it. It's not like 2 1/4 volts, or it's exactly 3 or whatever. So that it is a logic compatible device. Over here, we may put 3 volts worth of charge, and I'm sort of mixing my physical metaphors here, but you know what I mean. Like, so you may have charged this up to 3 volts. When you come back to it a little bit later, and it's like 1.9 volts, and you're like, oh, is that a 1 or is it a 0 that's been charged an awful lot up? You need some kind of external electronics to do an analog to digital conversion. And that takes time. And again, we're talking about how few electrons that are on here that are extra. I can't just get my multimeter probe wires and stick them on the side of it, because by doing that, just the amount of wire that I'm connecting to these will discharge the thing, and we can't tell if it's a 1 or 0. So there's a lot of complicated analog electronics that take a while to be able to read a batch of cells together by preconditioning all of the tiny, tiny, tiny cables inside the RAM chip itself to be like somewhere between 0 volts and 3 volts, and then doing their analog to digital conversion, having connected in the cells it wants to read. And then, funnily enough, once it's read, maybe say 512 cells, 1024 cells altogether, it stores them in a little piece of memory, just a tiny bit of memory at the edge of the chip that holds regular flip-flops, so just a 512 bits worth of this static RAM. And that's what we actually read. So when you're then reading the pins, when the CPU is actually talking to the pins of the DRAM, it's talking really to an array of just a few static RAM cells on the edge of the chip. And so having done that read as well, what happens is the output of that static RAM is fed back into the circuit. So that means that having done its determination, is this a 0 or a 1, it now uses the logic power from the edge thing to re-top up the 1s and to re-drain the 0s. So it kind of works for itself. So effectively, by reading a batch of this memory, we've actually refreshed it. But all of that takes time. And, that is a problem, because our computer is running, as we talked before, somewhere, 2, 3, 4 gigahertz, which gives us half or a third of a nanosecond every clock tick. And this kind of physical stuff takes a long time, like literally, hundreds of nanoseconds to kind of get things warmed up, prepared, read, pulled out. So we've got this giant array of capacitors and transistors that have all this care and feeding, which, some automated circuitry can do some of that, but they're slow to read. And we have some amount of this static RAM available to us, and we would really like everything to look like this. This would be great for us. We can access it. So what can we do to solve the problem of we want all memory accesses to be fast, or as many of them as possible? And the way that it's solved is to use a small amount of this memory as a cache for the external, much larger memory. So how on earth can we do that? How can we take the values that are stored in an external RAM chip and sort of hold them closer to us in this faster memory, but do it in a way that itself is very fast, right? I could, the first thing you might imagine you would do is you say, well, I'll just keep 16 kilobytes, say, of the fast static RAM, and then every time I go to read from the main memory, I have to search through all that 16 kilobytes of RAM memory and see if the memory that I'm trying to access has actually been copied locally. And that's great, but we only have about a third of a nanosecond, or maybe 2/3 of a nanosecond for 1 or 2 clock cycles, and you can't, even with clever silicon design, you can't search that amount of memory. We're in a world where we have to use a few logic gates to make a quick decision. And so the solution that most chip manufacturers come up with is to have a set amount of cache memory. Let's say we've got, I'm going to do this using decimal numbers rather than binary numbers, because then it's a lot easier for us humans to understand, but you have to realize that really it would be done with a certain number of bits. But so we want to read a memory address, something like 1255284. So this is what our computer has decided to read. It wants to read the memory that's at this cell. Now, the first thing we're going to do is we're going to say, well, there are economies of scale here. If I have to actually go and read from the real memory on the outside of the computer, I might as well do it in a decent-sized batch. So what I'm going to do is I'm going to group every 10 memory cells together. Again, 10 because we're humans, not it would be 16, 64, 128 for computers. So instead of me thinking of this as being a memory address that's 125284, I'm going to say, well, this is some kind of block 12528, and it's the fourth cell inside that block. And I'm going to treat that cell as the unit for which I'm going to either go to memory or I'm going to look in my cache for. And then having got that cell, I'll look at the fourth one if I want to look at that particular byte within the line. And, we've talked about robots shoveling stuff, right? Again, well, that means that we can give a robot that's going out to memory a very wide shovel to pick up 10 bytes at a time, which is a lot more efficient than picking out single bytes at a time. And it just happens to work well like that from the electronics point of view. So we call this sort of block that we're going to read from memory, that's a line, a cache line. And again, in a modern computer, that's more like 64 bytes, maybe 128 bytes, depending on whether you're on ARM or Intel or various things like that. But ours are 10. But we still have a problem here. We've got 12528, and somehow we've got to look for that somewhere in an area of memory. We've got, say, 16,000 entries. Actually, it won't be 16,000 again. I can't help but thinking computer numbers here. It'll be some human number. We're working out. So what I'm going to do, I'm going to have a number of slots, and each slot can store, let's say, 4 entries. Okay, so, and I'm going to say this is going to be a tag, and then this is going to be my 10 bytes of the actual cache line, and then we're going to put some flags on the end here, which we can talk about perhaps at the end. This gives me 4 possible places to look for my cache line. And then I'm going to have lots of those. So you have to imagine that there's a huge number of these, each of these 4 entries. So each of these is a cache set. So these are sets. And each set has, in this instance, 4 ways. We're going to call those ways. Those are 4 possible places that my number might be stored in. And what we're going to do is, let's say we're going to have 100 sets. That makes life easier for me. So this particular cache memory is 100 sets times 4 ways, 400, times 10 bytes. So it's 400 bytes of cache memory we're managing here, right? What I'm going to do is I'm going to take 2 digits of my address. In this instance, I'm going to take the 2 and the 8, where the 4 here is our index within the 10 bytes. That 2 and that 8 is going to tell me which of the sets to look into. And so I'm going to look into set 28. So this is set 28 now, as I've drawn it. And there would obviously be, 100 more, or whatever, sorry, 71 more. Maths is hard. So immediately we've taken our problem of, do I have to search every single cache location for 125284 down to, I only have to check 4 possible places because I've already indexed it in 28. So this 28 is already selected as a much smaller problem. And now we're in the domain where I can have the remaining digits, which in this instance would be 125. I can compare those 125 against the 4 possible things that might be in this cache. So let's say this cache there's something that is, 100 over here. This is 197. And then 202. And then, of course, then we would have, our, 125. Maybe, right? So this is obviously the cache as it is when we're reading it. And so our comparator can run, and we will do 4 comparisons with just logic circuits, and they could all run together. And in this instance, one of them would say, I've got 125, and then we would know that the number we're looking for is the 4th byte in here, 1, 2, 3, 4. So that would be the value we'd read right there. And again, this has now happened with very minimal amount of logic. We haven't had to search 400 possible ways. We've only searched 4. We've got a drawback here, which is now that instead of all of the cache being available for every possible memory location, we've said that, like, essentially these 2 digits of the address tell me which area to look in. But it means that if there's different areas of the program that are fighting with the same address here, then they have to fight over the same 4 ways of the cache. So that is how our cache can track quickly where to look. Now, obviously, if this wasn't 125 in this particular instance, just make that clearer, that those are kind of how we've broken our number up, then we would trigger a read to the real memory, and our robot with his big wide spade would go off and come back with the value. And then we would look at the cache set and say, which way should we replace now? Because we have to throw away what we had before and replace it with something that we've just fetched from memory, which there are different ways of doing that. One way is to just pick one randomly and just say, well, tough luck. Another way is in this sort of flag section over here is to do a count of how recently it's been accessed, and then the least recently accessed one you can throw away and say, well, we're going to replace that with my new cached entry. So far we've been talking about how we read from memory. You read through, the value comes from memory, we look in the cache, it's there, great, fantastic. If we're writing, obviously if it's in the cache, we can just update the cache memory over here and say write the value 99 in this value in this slot, but we have to note that we've made a change to this line of memory. So we put a little flag here that says it's been changed, and what that means is when this gets evicted from the cache, when someone else comes in and needs to use this particular slice, we can't just throw it away. We actually have to send the robot with the shovel out with the numbers that we have to go and put them into the real memory of the computer. That obviously is a little bit slower than just discarding it, because you have to wait for this to become free, you have to put it into memory, wait for the memory to come back. But by and large, that works out much better. So this memory can be accessed in single digit cycles, so 3-4 cycles from the point at which a CPU instruction needs to be able to read the memory. It can get access to this cache, and provided it hits the cache, that is, it finds the information it wants, the answer's ready in those 3 cycles. And that obviously is hugely important. And if not, obviously we go out to memory. But we actually can say, well, why about we have a slightly bigger cache to cache the cache, where it takes longer to search because it's bigger, and it can have more capacity. And so you have a second level of this that's bigger, that maybe has 1,000 sets, and each set has 8 ways. And now you've got a lot more memory. And then you go, well, if it misses the second layer of this cache, what do we do? Well, if it worked for the first time, let's put another cache on the cache. So most CPUs have 3 layers of cache before they get to memory, because memory is so much slower than this kind of static memory, this cache RAM, that it's worth putting large amounts of this on the chip. And in fact, if you've ever seen those beautiful shots of a CPU, when someone's holding up those platter of circular wafer of silicon with all the CPUs on it, if you can see a large repeating structure that just looks like a sort of same area filled in, that's all cache memory, right? All this stuff here, it's very repetitive, it looks the same. And most of the chip real estate is actually spent on the transistors that make up the caches, because that is where most of the time is spent, is going out to memory. So avoiding it at all costs is really important. And I suppose I should say why this works as well as it does, because it does in general work very well. And there's most programs want to access memory in predictable ways. If, for example, I was taking our Fibonacci program from the very, very beginning of this all, we're looking at memory sequentially one after another. And that means that, first of all, our efficiencies of scale means that when we go and fetch the first number, we actually go and fetch 10 bytes worth from memory. We pay the cost of getting 10 bytes, but it's not much more than getting 1 byte from memory, because once we've done all this measuring and voltage comparison or whatever, we've got a whole bunch of memory. So we do that once, we've got it now available to us in our cache, and now the next 9 bytes of our read are essentially free, right? They come out of this cache. We don't have to go to main memory. And most programs exhibit that kind of behavior. And we call this sort of physical locality. So they're locally accessing physically similar areas of memory, and so they're likely to be pulled up in a block when we get blocks from memory, or they go back and look at the same memory again. And that sort of looking back at the same memory again is more like temporal locality, so in time. If you're going to look at the same memory over and over again, it's obviously beneficial to have it inside the cache. So temporal locality means we're going to look at it in a short amount of time, and then physical locality means that it's likely to be near some memory that we've already touched. And that's very common.
Do things get bumped down a level if they're not used rather than deleted? It's sort of overwritten, but is it just moved into the next level?
Different caches do different things. But yes, largely, yes, the caches, the bigger cache holds all of the stuff that's been evicted from the lower cache. So the level 1 cache will have like a 16 kilobytes or 64 kilobytes or something like that. Then there's like a megabyte maybe of L2, and then there's like 10, 15 megabytes of L3. And then, when it gets evicted, we don't actually have to write it back to the main memory necessarily. We can just write it to the L2 and then get on with our life if it missed the L1.
Is that how things kind of waterfall down then? Or do you, when you go to main memory, do you put it in all 4 caches, or do you go, right, okay, we need this now, so we put it in this cache and then it gets...
That is a very, very interesting question. So it depends very much on the architecture of the computer and the choices that the folks who designed the system made. So until maybe 5 or 6 years ago, I think, Intel caches, so for the x86 family of computers, they had a policy where if it's in L3, it must necessarily be... other way around, sorry. If it's in L1, it must necessarily be in L2 and L3. That is, it would populate all of the layers, and it must be true that, all the higher layers have the same copy of the information. And they did this because then when they're evicting something from L1, they're guaranteed that it exists in L2, and they can just put it in the slot that it currently has in L2. And that makes it very quick and easy to do that. I think AMD chips decided not to do that way, and I don't know what ARM does, but this is kind of one of these microarchitectural decisions that people make. The downside of that so-called inclusive cache, where everything is included in the higher levels, is that if for whatever reason something gets evicted from the L3, then it necessarily also has to be evicted from L2 and L1 in order for the invariant that it's expecting to hold. And we haven't really talked about this, and it gets a lot deeper very quickly, but these caches are shared between, or some of these caches are shared between other CPUs on the system. And you could imagine that might be a problem where if one CPU has changed the value in its cache and another CPU doesn't know that, how do they agree on what the value is in a particular memory cell? And there's a very complicated protocol about it. But the level 3 cache is typically shared between CPUs. So it's sort of pooled amongst the whole chip, this huge array of like 16, 15 gigabytes megabytes, sorry, of L3. But what that means is a program running on another CPU might be running through the L3 and eventually evict something that in the L3 that's important to my program. And because it's been evicted from L3, it gets evicted from my L2 and then from my L1. And then when I go to look for my memory, it's not there anymore, and I have to take the expensive fault. And when I used to make trading systems for a living, that was a real concern and consideration. We had to make sure, you want your program to be as fast as possible. You don't want some random person logging into the computer that you use for your trading system, moving the mouse around, and that happens to evict the really important cache line that you were relying on for your trading system. And then suddenly something happens, and now you're very slow, hundreds of nanoseconds. So yeah, there's a lot of complex interactions with that, but you're right, it's an interesting thought that you have to consider, like L1, L2, L3. There's also something called a victim cache, which sounds pretty miserable, and it's a place where in between the last level cache and memory, the most recently thrown out information is stored in a sort of holding pattern. I'm not so hot on that, but it's remarkably effective.
When I used to install video television broadcast systems,
we
discovered that some of the video playback servers, so we're talking about very specialized bits of kit which any laptop could do now, or a Raspberry Pi could do now, but 20 years ago you had this very specialized system with multiple video cards to play out digital video, and they were installed with a version of Windows that came with everything like Minesweeper and Solitaire, and we'd spend time in the rack room, in the in the apparatus room playing Solitaire, until one of the managers spotted us one day and went, "You're not doing that on the video server."
Oh no!
You can just imagine that. How good is Windows at managing this? Anyway, that's another question.
No, that's a really interesting. But yeah, when you're talking about stuff that has hard real-time deadlines, like delivering every 60th of a second or 50th of a second, you need to present a new frame to, I don't know, the entirety of the UK. Then maybe you shouldn't be clicking around in Minesweeper.
The system's in a test state at the time; it wasn't actually live. But the point remains that these games were playable on a machine that could have been live. Yeah. Anyway, sorry.
Same deal. I mean, and it's the same deal. You administrate. The system administrator of that system has to be able to update the software, has to be able to log in and debug and diagnose. So all these things are possible, and you have to. At the very extreme, most people most people don't even need to think that there's a cache inside their computer, even if you're a programmer. You know, if you're writing Python code, it's possibly not something that you are exposed to. But there are some things that you can do that make it very much worse or very much better. So again, if you know that you can arrange your program to read from the beginning of an array of numbers and just go linearly from one end to the other, then that's going to be better because the cache will helping you. And one of the other things that caches do, so there's some circuitry in the L1, L2, and L3 that spot patterns in misses, and they go, wait a second, you keep looking for the next 16 bytes every time. Why don't I just start getting ahead of you and ahead of time pre-fetch, that is to go to the memory, and even though you didn't ask for it, and say, hey, can I have the next 16 bytes? And then it would write it into the next cache available slot. And then when you come to read it, it's already there. And that's kind of even more miraculous, right? Unfortunately, that can go wrong where it kind of detects a pattern that doesn't really exist. And now your memory traffic is higher because your cache is ineffectively pulling down information it doesn't realize you won't need and flushing things out that you do need. I was trying to think of a way of expressing what these two types of memory look like. And so a flip-flop, if you think of, is a snap bracelet, right? This is a 1 and it's stable. Once I put it into a 1, it is stable in the form of a 1.
Yes.
But if I apply a little bit of voltage, then it'll curl up into a 0. I'm trying to hold this up to the camera so you can see it. And now it's stable as a 0. And if I want to put it back to a 1, I put a little bit of extra oof into it, and now it's back to being a 1 again. So what this doesn't unfortunately show is it doesn't show that this takes up power all the time, right? You know, I can leave this on my desk and I don't have to plug it into anything. It won't disappear off or anything like that. So that's where my analogy breaks down. But thinking putty, or silly putty, or whatever it's called, is this amazing substance that will gradually sloop back down into being a flat, like, puddle. But I can make a little 1 like this out of it, and if I put that down on my piece of paper here, so that's probably better on there, it's a bit like a slug now, but that's a 1. But if I'd have done this at the beginning of the presentation as I'd planned, by the time we got back to it, it would just be a big splurp of like a puddle. Or, you know, again, of a 0 like that, there's my little 0. It would again be indistinguishable from a puddle after, you know, like 10 minutes. And at the sort of scales we're talking about, like we said before, you know, in the previous thing, you know, that's about the time. That's about 60 or 70 milliseconds. And that's how frequently these things have to be topped up, right? So behind the scenes, your dynamic memory is being topped up every 50, 60 milliseconds in order to keep the memory from decaying away. And of course, milliseconds sound really quick to us. You know, I can't, you know, that's like a blink time. But to a computer, that's actually quite a long time. So it's not actually that big a deal, but it is noticeable, right? You can tell that sometimes the memory controller is busy saying, no, I'm just making sure your memory hasn't decayed. And, you know, just as a sort of security note here, there have been issues where certain patterns to memory controllers can upset them so badly that even though they're refreshing regularly, that you can force charge to leak out into adjacent cells by reading and writing certain patterns to memory. And that can actually cause security issues. There was a whole furore about this maybe, I'm terrible at, you know, 5 or 6 years ago. It was called the row hammer attack. And it uses a particular way that you talk to the memory to like, on purpose try and disturb it and put it into a worse state where it'll actually leak charge between cells, and then you can actually like change memory that you're not supposed to be able to change, which obviously is a huge deal. So you know, there's been some mitigations put into place now. I think memory now on purpose refreshes are much more often than that in order to prevent this attack from being viable. But yeah, so that is how our robot goes and gets the memory from the big old pigeonholes, which unfortunately aren't pigeonholes. They're very complicated looking circuits like this, or there's some analog to digital circuits that look like this.
Well, basically, it tries to avoid at any cost going to those pigeonholes by the sounds of it.
Exactly, yeah. Actually, you're right. Yeah, he has his own little notebook that he carries around with him that has like the last 400 things he's done in some kind of way, and that's what he actually wants to look into and avoid going, as you say, to the pigeonholes.
I've got it in a pocket here somewhere.
Yeah, that's right. It ends in this sort of register renaming step, and now there's this big sort of melee of robots just doing as much work as they possibly can. And at the very end, we have something called retirement, where the instructions are finally written out, and that happens in the order that the program wrote them in, regardless of how